Okay, so yeah, you cannot use, this is not a candidate for the integral test or the comparison test because of the negative terms that are involved. There are some negative terms. So this is just kind of, I'm trying to give you a problem that you can't solve so that you can see that we need more tests. So far I've only given you integral test, the comparison test, and the nth term divergence test, but that's not good enough, evidently, because then we couldn't solve this problem, right? So you guys know that some series will alternate their signs so that every term has the opposite sign of the previous term. So it goes positive and negative and positive and negative and positive back and forth. Actually, minus 1 to the n will cause this to happen. So if you see one of these in your summand, it's likely it'll cause alternating like this. Another culprit might be if you see negative 1 to the n plus 1, that'll cause the series to flip back and forth between positive and negative. Or if it's negative 1 to the n minus 1. Here's another one that causes alternating signs you might not have thought of. Cosine pi n. If you see a cosine pi n, every time n is an even number, you get 1. Every time it's an odd number, you get a negative 1. So this, too, is actually the same exact alternator as negative 1 to the n. Cos pi n and negative 1 to the n are exactly the same thing. They both produce minus plus, minus plus, minus plus, minus plus. Okay, and then the last one is sine of odd multiples of pi over 2. So if you see a sine of 2n plus or minus 1 times pi over 2, that also will cause alternating. For example, if you plug in 1, you get sine of 3 pi over 2, that's negative 1. If you plug in 2, you get sine of 5 pi over 2, that's positive 1, you see. So it's going to flip between 1 and negative 1, back and forth. Okay, so anything that has these in it could be alternating series, and if they're alternating series, they have negative terms in them. Now, certain alternating series will converge, and any alternating series that contains the following two features will converge. Here are the following two features. Scroll up a bit. First, the limit as n goes to infinity of a sub n must be 0. Okay? Now, quick word about what is a sub n. If you see a series that looks like this, okay? Which is actually the one I started you off with. A sub n is this part only. Okay? So be careful what you view as your a sub n. Circle everything except the alternator. Okay? That's a sub n. So the first rule is that part needs to be something that when you take the limit as n goes to infinity, it goes to 0. Okay? The second rule is that a sub n plus 1 has to always be less than or equal to a sub n. Now you might say, Mr. Shore, that's the same exact thing. What you just wrote means the terms are getting smaller. You're right. This means the terms are getting smaller. This means that A100 is less than or equal to A99. And A1000 is less than or equal to A999. In other words, the terms are diminishing. This is saying the terms are diminishing to 0. This is saying the terms are diminishing. Isn't this redundant? Not quite. There are some things that go to 0 over time, but they do so by wiggling up and down, up and down, up and down. Okay? I know it's kind of a gross analogy, but if someone is dying, right, and you watch their heart rate, it will eventually flatline, but it might spike a few times before it hits the flatline, before they actually die. So that would mean that there's some spikes in the behavior, and we don't want that for this kind of problem, okay? So an alternating series must not only diminish towards the x-axis, the n-axis, but it also needs to do so monotonically. So I'll draw a picture of what this means. If you get rid of the alternator, and you just look at a sub n here, it needs to be doing this, not this. needs to approach 0, and it needs to do it in one direction. In a monotone way. One direction. Yes?
So is it usually sinusoidal functions that satisfy the first feature but not the second, or is it?
The sinusoidal, for example, you could have like n equals 0 to infinity. Let's do n equals 1 to infinity. Sine n over n. See, this wouldn't be an alternating series.
Because it has that.
Well, if you plug in 1, right, you get sine 1 over 1, which means sine of 1 radian over 1. In other words, sine of about 60 degrees divided by 1. That is a positive number. But if you plug in sine of 2 over 2, that too is a positive number. Sine of 120 degrees divided by 2, see? So it's not truly alternating like it's supposed to. So today's discussion is only for those series that alternate between positive, then negative, then positive, then negative, back and forth, back and forth. Okay? All right. So don't confuse sinusoidal behavior with alternating behavior. It's a little bit different. All right, let's go to this drawing one more time. I just want to say it one more time. The conditions are this. This curve must be approaching 0, and it must be doing so without ever rising. That's the rule. The two rules. Okay? So we call this decreasing monotonically. Let's write that. Okay, new word. Decreasing to 0 monotonically. Question?
Are you recording?
I thought so. Yes, I'm recording. Thanks for asking. It's important. Okay. Now, we do have a little bit of forgiveness on series. For example, if a series is misbehaved, then let it be misbehaved for a while, but straighten itself out. Okay? For example, if this is going up, down, up, down, up, down for a little while, but then later on it decides it's going to just monotonically go down, it's still a candidate for the alternating series test. Okay? So it's still on the board, on the table today. We can still talk about it. But if it forever misbehaves and it forever has this tendency to spike back upwards and then come back down and spike back upwards, we don't talk about it. Okay? It's not passing condition 2. What's that? Yes, right. So some series, some series will correct their behavior. They'll act goofy at first. You know, we saw this too with the DCT. We were trying to compare one series to another, and we saw that it was term by term greater for a while, and then after like the 6th term, it became term by term less. From that point on, it was term by term less. So we allow for that. Here's the reason why we allow that, guys. If a series is divergent, that means it adds up to infinity. You can try to rescue that by subtracting off a few numbers, but you'll never be able to rescue divergence by subtracting off a few numbers. In other words, you're going to have a series that's divergent, but the first few terms are negative. Well, it's still divergent. Sorry, infinity minus 10 is still infinity, see? Also, if the series is already convergent, if the first few terms are misbehaved, it'll just change the convergence value. It will not change the fact that it's convergent. Okay. So we're not too strict with series, but we have rules about their infinite behavior. Now let's go to this first example. We're just trying to see if this converges or diverges. There are two conditions, two things to check always. Technically 3. The first is you have to know it's alternating. So let's look at example 1. Is it an alternating series? Would it switch between positive and negative consistently forever? It would. Who's the culprit? Negative 1 to the n is the culprit. So circle your alternator, and then circle everything else. Everything else is what you're actually going to study. So you're going to actually study this part. This is the a sub n. Okay, condition 1 requires that the limit as n approaches infinity of n over n cubed plus 1 be 0. Is this a true statement?
Yes.
Yes, this holds true. Okay, so it passed the first condition. It also requires that an plus 1 be less than or equal to an. For example, a4 should be less than or equal to a3, you see? And a5 should be less than or equal to a4. The terms should be getting smaller. So I wrote out a few of these. You normally just do this part in your head, but I tried plugging in 1 and 1 plus 1. In other words, 1 and 2.
and I got the following. I got 2/9 is less than or equal to a half. Is that true?
Yeah.
It is. It's 0.22 versus 0.5. It's true. So this is true. Then I tried plugging in 2 and 3, and I got 3/28 is less than or equal to 2/9. Is that true?
Yeah.
Yes, it is. If you need a calculator to verify it, that's fine. The next one I plugged in 4, and I got 4/65 is less than or equal to 3/28, and that's true as well. And the next one is 5/126 is less than or equal to 4/65. That's true. They're all true. In other words, what's happening is this sequence we've just shown, not only is it going to 0, but it is also going to 0 monotonically. No spikes. It's always a little bit lower than it was before. So we would say that by the AST, the alternating series test, since both conditions are met, we have convergence. Notice that most of this test can be done in your head. All you have to do is kind of ignore the alternator, look at the limit there and say, is that 0? That's pretty easy to answer without any calculations. After you determine the limit at 0, just make sure it's the kind of fractions that are getting smaller, which you can sort of do in your head, and then you've got your answer. If either condition fails, we have divergence. Okay? Now we would never do this process on a non-alternating series. I told you before, we never use just a pure limit to study a series. This is the exception. With alternating series, we can do that. Okay? Just check both conditions. Feels like you're almost doing a limit problem. Not too hard. Let's go to the next one. You can find your alternator in this problem. It's the -1 to the n again. Right? So there's your alternator. But here's the actual series that we're going to study. 1/n, you see. 1/n. I mean, that's the actual a sub n we're going to study. So a sub n is 1/n. Let's see if it converges. First, we take the limit. Is this 0? Yes, it is. Is 1/2 greater than or equal to 1/3, which in turn is greater than or equal to 1/4? And is that greater than 1/5? In other words, are the terms diminishing? Sure they are. You know, they go 0.5, 0.33, 0.25, 0.2. It is decreasing. In fact, you guys even could sketch this sequence. 1/n just looks like this. It decreases monotonically. Notice I've taken out the alternator. Everything's above the x-axis here, right? Okay, thus the series converges. And you might notice something. This is just the alternating harmonic series. It's really just the 1/n series, but it has an alternator in it. Now the graph I drew for you is not the graph of the alternating series. It's the graph of the series without the alternator in it. Okay? Let me show you what the graph of the alternating series looks like. Here's the graph of the one without the alternator. This is length 1, this is length 1/2, this is length 1/3, this is length 1/4, and so on. And you can just think of these as little segments. You see? The alternating one actually looks like this. This segment is upside down. The next one looks like this. The next one's upside down. The next one's right side up. So here's what we're saying. This is really, really important you get this. We've studied this series before. We've studied this using integral tests, and we said it diverges. What that means is if you took all these little segments and tried to stack them together, it forms an infinitely long segment with no true measurements. Okay? This one, since some of the distances are counting as negative, when all of these are added up, you actually do get a finite value. So that's what convergence means. It means if you stack these pieces together, you either get an answer or you don't. If you stack all the positives together, it forms something way too long to study. But if you count up and down, and you stack the positives going upwards, and you take the negatives and stack them downwards, it creates a segment that sort of balances out to actually come out to some value. Okay? So it's no surprise, I guess, that adding an infinite number of things would create infinity, but if we have subtraction subtraction involved, we could get something finite. And that's exactly what's happening here. This one's really important. You need to know that the alternating harmonic series converges and the harmonic series diverges. So write divergent on this picture, convergent on this picture. Okay? You'll use this one again, I promise you.
Wait, can you repeat what the sentence?
Yes. The alternating harmonic series converges. I also have it written right here. Even though the harmonic series itself is divergent. That's this one. This one's divergent. The alternating version is convergent. This happens sometimes. You'll have a divergent series, but when you stick an alternator in there, it converges. It's because of all the subtraction that gets introduced.
So it turns into a telescoping series pretty much?
Kind of, yeah. Kind of. That's a good point. We've got some cancellation there of distances and stuff. Yeah. So the takeaway on that problem is the alternating series converges. The alternating harmonic series converges. Let's go to the next example. We won't have a takeaway on every problem. Look at this one. Does it converge or not? Well, the alternator is a little hard to find. So I suggest we write this problem like this. And then we'll just put the minus 1 to the n over here. It doesn't matter where we put the minus 1 to the n. Remember, negative 3 to the n is the same thing as negative 1 times 3 to the n, which in turn is negative 1 to the n times 3 to the n, right? So there's no reason why we can't just suck out the negative 1 to the n and stick it in front, see? Even those on the bottom, we put it in the top and the front. Doesn't make any difference. The point is, our a sub n is this part. See? So you want to identify that a sub n, because that's what you're really studying. Let's check condition 1. Is LIM, n goes to infinity, of n over 3 to the n really 0? What do you guys think? Do you think that goes to 0? Yeah, you could actually use L'Hopital's rule to defend it. Because when you take the derivative of the top, what do you get? 1. When you take the derivative of the bottom, you get? Good, 3 to the n ln 3. At that point, it's clearly bottom heavy. All that you have on top is a 1 now. So I agree it goes to 0, so I'm going to put yes for this. Let's look at condition 2. Is 1 over 3 to the first larger than 2 over 3 to the second? And in turn, is that larger than 3 over 3 to the third? Yes. That too is true. 1/3 is greater than 2/9, and 2/9 is greater than 3/27, which is 1/9, right? So it's on. And this is monotonically decreasing. Thus, the alternating series converges by the AST, the alternating series test. No takeaway on that one. Okay, let's move on. Determine whether this series converges or diverges. You can clearly see a sub n is just sitting right there. Circle that. This is an interesting one. If I ask you, is the limit of n plus 1 over n equal to 0? The answer this time is no. Who cares about condition 2? This alternating series failed condition 1. I'm not going to test condition 2. I don't care. It's divergent. Okay? Now, you didn't need today's lesson to help you with that one. You could also have said that this series diverges by the nth term divergence test. In other words, 3 days ago or 4 days ago, I could have given you the same problem. And you would have looked at it, you would have probably included the alternator because you didn't know what to do with it. And you would have declared it to have no limit. And you would have gone with divergent. So, that was not really new, but you can see how the alternating series test confirms it. Question or comment? Should I pause the video? Go ahead.
So, if you were to get yes for the top, but no for the first few, how would you know to keep testing?
Yeah, that's a good question. It can get to the point where you have to actually prove somehow that it's monotonically decreasing. So, let me okay? Well, I guess I don't have to pause it, but they are kind of hard to do. It's okay, it's a good question. I mean, how sure are you that it's really decreasing on every single term, right? Give it a second. And we'll go back to example 1, actually. This software is a little slow. I just need a place to scribble here. Okay, let's go back to the first example that we did today. In the very first example, you had this series. And I showed you that the first couple terms really were getting smaller than the last few. But if you really wanted to show that this was monotonically decreasing, here's what you'd have to do to really prove it. Watch close. You would have to show that n plus 1 over n plus 1 cubed plus 1 is truly less than or equal to n over n cubed plus 1. But how do you prove that? Well, you would probably use an inductive proof, actually, which we haven't talked about in this class. I tried to convince you that because 2/9 is less than or equal to a half, and 3/28 is less than or equal to 2/9, and so forth, since it seems to be true, then it was true. But what he's asking is, suppose the first few terms had been disobedient to that, how would we know later that it was going to start obeying that? So what you can do is you can go ahead and cross-multiply these, because the only time you're not allowed to cross-multiply an inequality is when there's a chance that something's negative, but these are all n values, so we should be totally legal cross-multiplying here. And you get n to the 4th plus n cubed plus 1, when you multiply this way, is less than or equal to n times n plus 1 cubed plus 1. I worked this out earlier, so I know the solution. This is going to be n times n cubed plus 3n squared plus 3n plus 1 plus 1. So you'd actually have to go through some kind of a process like this to show that it's monotonically decreasing. N to the 4th cancels. Collect all terms to one side. You have 2n cubed plus 3n squared minus n minus plus 1. Is this less than or equal to 0? Then you could graph this and show that it's always above the x-axis. At which point you then know that this statement is true at all times. This is true for all n. Therefore, this is true for all n. Or you can use an inductive proof, which is a 4-stage process. But it's a good question. So I'm going to just let you go with your gut feel. If you feel the numbers are getting smaller, then they are getting smaller. You can trust your gut. Okay? Try the first few. Pat your belly if it led you to the right answer. Okay? I don't know why. Let's go on to the next one here. How about this series? And I give credit to the Larson textbook. I borrowed most of my examples from Larson. I don't know where my Larson book is right now. But awesome book. Yeah, it's right here. Larson's textbook, Larson and Hostetler, standard college textbook. Excellent textbooks, not an AP prep book. It's just a real calc book. And Series, he does an awesome job with Series. And I'm following all of his stuff for this chapter. You can see we're not really using our book that much, right? Okay, let's talk about this series, though. Look at the numbers. We have 2 over 1 and 1 over 1 and 2 over 2 and 1 over 2 and 2 over 3 and 1 over 3 and 2 over 4 and 1 over 4. Then so we're going to have 2 over 100 and 1 over 100. Are these numbers getting close to 0? 2 over 100? That's pretty close to 0. Eventually we'll reach 2 over 1,000 and 1 over 1,000. These are small numbers, and they're getting smaller, and they're getting closer to specifically 0. So the limit here is going to 0. I would say that checks out, but here's the problem. It's not a monotonic decrease. Look closely. 2.0, 1.0, 1.0, 0.5, 0.66, 0.33, 0.5, that just went up. 0.25, 0.4, that just went up. We just went up from 0.25 to 0.4. So it's not decreasing monotonically. Sometimes it jumps up a little, sometimes it jumps down. So we would say fails condition 2. It's especially obvious when you write the decimals in here. Do not look at the negatives when you study this, okay? Remember, we do not look at the negative. Whatever alternating signs there are, we ignore that when we study the numbers, right? So that's why I'm circling just the fractions and not their signs. But sometimes it does jump from 0.25 up to 0.4, you see. So this one's divergent. Question?
Oh, so it's divergent?
Yes.
Never mind.
You were going to say the same. Okay.
I was thinking, well, I mean, obviously it's wrong now, but it's kind of like if you do take into account the negatives, it would be approaching 0, right? Because it would be 2 minus 1 over 1, and then 2 minus 1 over 1 half, or like, and then it'd be 1
Yeah.
half, and then 1/3.
Yeah, there's ways to pair these up where you can start to see that it might converge, but it doesn't technically converge because of the two conditions. Now let me show you. If you looked at this one a little bit closer and you had looked at it in pairs, maybe you had a keen eye for this sort of thing. If you had noticed this, there is a pattern. It goes 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5. See that? In other words, it seems like you've got a 2 over n. And then there's a minus. And then look at these greens. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. See that? These are just 1 over n's. But this is the harmonic series in disguise, isn't it? Well, no wonder it's divergent. So it looked like an alternating series because of the way it was written, but it really is just the harmonic series in disguise when it's grouped together in pairs. So this one is divergent for that reason too. It's really a harmonic in disguise. All right? So don't be fooled by the plus minus thing. There are two conditions to check. Cool example from Larson's book there. Let's go to this next page. Now, if you see this symbol, absolute value, you can pronounce it without alternating. Okay, so let's read the sentence that way instead. If the series without alternating converges, then the series converges. So I'll say that again. This is a very profound sentence, so listen carefully. If a series without alternating converges, then the series with alternating will also converge. We call this absolute convergence. This will make really clear sense to you in just a minute. Which is more likely to converge, guys? Let me ask you this. Which is more likely to converge? Something whose plot looks like this. Blue or red? Which is more likely to converge? How many think the blue one is more likely to converge? How many think the red one's more likely to converge? Okay, the problem with the red is when we start to add up all the red segments, the thing gets longer and longer and longer. See? Here we have some where the segments are pointing downwards and they count as subtraction. So this is much more likely to converge with all the negatives in there, see? Now what if I told you, listen, that these were the same series, but this one is this one up here is an alternating version of this one. And then I told you that this one, which is very unlikely to converge, does converge. If I told you this one converges, would you trust that this one does?
Yes.
Sure it does. If these segments add up to something finite, then certainly counting some of them as backwards would make it even more so finite. You see? So if this one converges, then we would definitely believe that this one converges. Heck, this one has minus signs in it. Subtractions. Keeping things finite, you see. Pulling off value. Okay? So these two drawings here might really help you understand this sentence. If the series converges in the red form, it will definitely converge in the blue form. Okay, hopefully that made some sense to you. Now, if the red one diverges but the blue one converges, then we call that conditional convergence. Some series will only converge if you put an alternator in.
Just like the harmonic series.
The harmonic series is that way. The harmonic series will diverge, but if you put an alternator in, it'll converge. Some series are like that. Some series will converge with or without an alternator. Some will diverge with or without an alternator. Does everyone know what an alternator looks like? -1 to the n. -1 to the n plus or minus 1. Cos n pi. Sine of odd multiples of pi over 2. If you see these guys, their only job is to produce a minus-plus effect, or a plus-minus effect. Okay? So my next several examples, I put them into a table because I thought that would help you more. When you're testing for absolute convergence, you're going to want to organize your work maybe like I have here. Okay, so let's go ahead and try this. I don't know. Oh, you wanted to go to the trash can instead. Okay. Let's take a look at this one. Teaching is fun. Bigger? Bigger. Okay, let's go bigger. Am I recording? Yes. Okay. Testing 1, 2, 3. Okay, first thing is you're going to be testing the series as given. Okay? So here is your series. Do we think it converges? There are two things you're going to try. This column is AST. Okay? First, identify the nth term. Forget the alternator. Just look at that. And let's do this in our head from now on. Okay? This is really easy to do. N over n cubed plus 1. Is that going to go to 0 if n is big?
Yeah. Yes.
Yes. So first condition, pass. Second, is every term less than the previous term?
Yes.
Yeah, 1 over 2, and then it's going to go 2 over 9. Okay, so it's going to definitely decrease monotonically. So this one is going to converge by the AST. We already did this problem. It was my first example. Okay? Now what about if I put in an absolute value? What does absolute value actually do? All it does is kill the alternator. Okay? So now we're on to a brand new series though. See, this is a different series technically. And you may not use the AST to study it. It has no alternator. Do not use the AST. You can use any other skills I taught you. Nth term harmonic, nth term divergence test, DCT, LCT, whatever. Integral test. Any suggestions? Direct comparison. What would you compare it to? Also known as? Okay, good. So by DCT, this converges. This converges because it is term by term less than the convergent series sigma n equals 1 to infinity 1 over n squared. This is the convergent series, P series with P equals 2. P series P equals 2. Convergent. This thing is term by term less than that, so it too must converge by DCT. Good. Now we got conditional or absolute convergence here. Which one did we get? It converged both with the alternator and it converged without the alternator. That's absolute convergence. Okay, that's absolute convergence. Absolutely convergent is the adjective or adverb there. Thank you. Look at this next one. Boy, that looks so awful, right? But what's the sine 2n plus 1 pi over 2's job?
Alternator.
He's just an alternator, so don't stress out about that. You're not even going to think about that anyway. just look at it this way. In fact, let's just write that for what it really is. It's just negative 1 to the n, same thing. But we're not focused on that when we do the AST. We look at what's left over after ignoring the alternator. Does 1 over 2 to the n go to 0?
Yes.
Yes. Does it do so in a uniform way, like decreasing always?
Yeah.
Yes. So this converges by AST. I forgot to write converge on my first one up here. Let me put that in. Converges by the AST. And this time we have to write that too. Converges by the AST. Let's look at the series with no alternator. Oh, this is an easy one. Think of it as 1/2 to the n. That's a known series. That's a known type of series. Is that a P series or a G series? No.
G series.
It's a G series.
Like the Gatorade G series.
It's like the Gatorade, yeah. It converges because it is a G series with R equal 1/2. R is less than 1, see? Coming back to you now?
Yeah.
Good.
I just wanted to kind of like a refresher. So like if P series has n greater than or equal to 2, it converges. Is that true? Or?
No, the rule is P series converge when P is greater than 1. P series converge when P is greater than 1. And G series converge when R is less than 1.
Okay, cool.
Yeah.
So P series.
Yeah, it's all coming back to you now?
Definitely.
Yeah, cool. All right, now this one, again, we got convergence in both cases, so this is absolutely convergent. Look at the next one here. Remember, the alternator is that cosine pi. There's your alternator. Forget the cosine pi. Just look at the ln n over n. 1 over ln n. Does that diminish to 0?
Yes.
Yes. Does it do so uniformly and decreasing like? Yes. So this converges by AST. Now look at the series with no alternator. This thing diverges because it is term by term greater than the harmonic. You might say, why is it greater than the harmonic? Well, because it has an ln n on the bottom, which is less growing than the n is. See? So this here has a bigger denominator. 1 over n has a bigger denominator than 1 over ln n. Yet 1 over n diverges. So that means 1 over ln n must diverge as well by dct. Direct comparison. I'm getting a little low on time, so I can't take questions on that one right now. But we did get a converge with alternator, diverge without the alternator, so this would be called conditional convergence. Conditional convergence. Does the series converge? If there's an alternator. This next one is the same answer, actually. You think of it as 1 over n. This converges by the AST. But without the alternator, it diverges because it's the harmonic. It's the harmonic series. Or you could say a P equals 1. P equals 1 P series, you could say. So this is conditional convergence again. I think I kind of messed that up a bit. Oh man.
Bad.
There we go. I had it on the wrong line. This is conditionally convergent. Okay, one more example on this, right? Isn't there one more? Yeah, one more. You can try it if you want. Okay, so this one, sigma n equals 1 to infinity, negative 1 to the n times 1 over n to the 1/3. This converges by the AST, but it diverges without that alternator because it's a p series where p is less than 1. Diverges because it is a p series, bless you, with p is less than 1. Again, conditional convergence. Okay, so I wanted to put my work in a table because I knew that there's a lot going on in this chapter, and if I just scribble a bunch of sentences everywhere, you're going to be able to follow as well. But now you can come back, and when you're doing worksheet 4, which you'll get this afternoon, you'll be able to find a problem kind of like it, here in the table and work it out. Don't be fooled by all this cosine pi and sine 2 plus 1, 2n plus 1, pi. Those are just alternators. You can just ignore them, actually, for these problems mostly. Let's look at this next one. There's one more thing that absolute convergence is helpful for. Remember I gave you a picture of red and blue. Okay? And I told you that anything with additions and subtractions is more likely to converge, right, than something with just addition. Okay? So at the top of the page, I stated this once before, but we never really used it. Let's use it now. Imagine a series that alternates, but you don't know how to study it. You can't figure out which test to use. It's not quite alternating properly or something. You could actually take the absolute value, test for convergence. If it converges in the red form, it most definitely will converge in the blue form with all that subtraction. So let's go ahead and try this next problem. So look at this next problem. It's a non-alternating series. Why do I say that? Well, if you plug in 1, you get negative half. And if you plug in 2, you get negative 1/4. But if you plug in 3, you get positive 1/8. If you plug in 4, you get positive 1/16. If you plug in 5, you get negative 1 over 32. If you plug in 6, you get negative 1 over 64. Is this an alternating series? Not quite. An alternating series switches every other term. Every term switches. Here you can see it's like 2 negatives followed by 2 positives and then 2 negatives. So you're not even allowed to use the AST here. You may not use the AST on this problem. However, if we kill the alternator to form a simpler problem, we can see it's really just a convergent G series. And if killing off the alternator we find a convergent series, then certainly with the alternator it will converge. And that's the end of the lesson. Okay? So if the series is too complicated, try killing off the alternator. If it's convergent without the alternator, it must converge with an alternator. That's what the theorem at the top is saying. You'll get worksheet 4 this afternoon.